Okay, so welcome back everyone, and hope you guys had a great weekend. And we are going to take today slightly easy because we are also almost wrapping up everything we set out to do, at least in the first half of the course. Throughout this first whole course, we're going to learn about different types of motion. And we set out for our first goal is to find out what makes things move and how do we make predictions about things move, right? So we are actually closing up to the end, and there is still a couple of remaining chapter, but within this week, we're going to wrap everything together and we're going to introduce new ideas and new concepts or even new types of motion as we go forward, right? And let's see where we are and where we're going. As I said, always good to keep that in mind, right? So we'll do that very quickly. And we started our journey by understanding forces. And because we want to know motion, right? And we realize force is really the thing that creates motion. That is the mastermind behind all of these things. Why do things move? Because things have forces on it. In fact, more accurately, force causes acceleration, right? Not just velocity. Velocity does not require force. Things have a velocity, they will continue with velocity. That's the main takeaway from the first week. Now in the second week, we go like, now, all right, now I know how to find the net force on some object. So I can find the acceleration. How do I do that? Easy, just divide by the mass, because the mass is what's preventing it from accelerating. The more massive it is, right? If I multiply, right, the net force equals to ma. The more massive it is, with the same amount of net force on something, the smaller the acceleration. So what is mass? Once again, mass is the prevention of something to accelerate. In other words, it's a measurement of the concept of inertia. Inertia is a concept. It's not something you can measure. The closest thing you can sort of quantify it, right? Quantity is something that you can measure, right? The closest thing, the closest number or quantity you can use to measure inertia is mass. In fact, that's what we call mass, it's a measurement of inertia. All right, so good, but what good is that? Right, so we have mass, we can find acceleration, but what good is that? What we really want is to find out what happens in the future, right? So armed with acceleration, there's no good unless we understand how to do kinematics, right? And that was the big part of our second week, right? So in the first week, we understand vectors, we understand forces. In the second week, we translate that to find that once we know A, we can know V, we can know X. In fact, we'll know the position and the velocity of objects at everywhere. And throughout basically the rest of your physics course, not only that, the rest of your scientific career, and not only that, throughout the rest of your life, pretty much, I challenge you to think about every question you have about the natural world. And I mean natural world, like scientific natural world. If you, a question that we cannot answer is, in physics, it's not part of our goal, is why is that person happy or sad? That's not part of our goal, although it's an important question, but we'll solve one thing at a time, right? We have a specific goal. Every natural process about a physical world. Why does the bloodstream go that way? Why do someone have high blood pressure, someone have low blood pressure? Anything you encounter that naturally happens about the physical world really comes down to motion. And any question in your rest of your career, why do certain person have blood clogs or certain people have muscle cramps? It's anything that moves originates from a force, right? So now you know how to analyze force. There's two types: contact force, non-contact force. We talked about all that. And once you get the force, why do we care about forces? Because we can turn it into not only acceleration, that's the direct link from Newton's second law, but we can turn it into making predictions of where things are at later and how fast they're moving, right? If the blood is not moving very quickly, then you have a low velocity and you have a problem because your heart requires blood to function. So all the things are about motion. So now, and then we specialized, right? We specialized, well, let's start with 1D kinematics, right? One dimension. So either things only go up and down or left and right, or at worst, down a slope. So everything just goes in one way. We spent the day looking at all those different things. All the things you might think it's very limited, but anything from the fall of an apple to the crash of a car. If you go in a car accident, things are usually going in one dimension unless you're crashing into each other in a roundabout. But as you can see, it actually is very applicable. But that's of course not the end of the story. And we move on to also talk about two-dimensional kinematics as well, right? So, and we specialize as well. We look at, well, out of all of them, we look at projectile motions as sort of the quintessential type of motion. All right. So that is so far what we have, right? You see where these things are, and things follow projectile motions because of force of gravity and nothing else. So that's a very specialized one, but again, very important. Everything from almost 50% or more of any sports you see in the Olympic involves projectile motions, right? What we are going next is going to look at the only thing. So for the goal for the rest of this week is really just to wrap up with showing you a couple of more examples, solving some different problems. That's the goal for today, actually. And then we are going to cover two more, not random topics, but two miscellaneous topics. The first one, not so random, actually follows this path as well. It's the second most important 2D kinematics types of motion, other than projectile motion, is circular motion. The majority of things that you see that's not projectile motion, another big part of it, I bet you, is circular motion. Every day you will go in circles because you live on the surface of the Earth. The Earth is spinning around, so you're going in circles. In fact, even if the Earth is not spinning around, it's going around the sun. So the Earth is going around the sun in basically roughly a circle, right? We're not gonna worry too much. Is it a perfect circle or not? And in this course, we'll study the basics first. If you're gonna be an engineer in the future, you're going to worry about the little deformations, or if you've been an astronomer and astrophysicist, yeah, you're gonna care about, is it exactly a perfect circle? I'm not gonna answer that. You can look that up if you're interested. Is the Earth's orbit around the sun a perfect circle? You can see that. Yeah, we're not gonna, but basically we're gonna study the basics of it. Let's assume things are a perfect circle. How can we make predictions about that, right? So it's an important motion. We'll look at that in tomorrow's lecture, I believe. And also, yeah, we will throw in a extra topics, sort of miscellaneous topic called universal gravitation. And this is a good way to end this sort of journey in the first half or the first 3 weeks of this program. And just a quick motivation of why we're going there is this. We have talked about weight as one of the special force. Remember, what's the definition of weight? Can you recite that? Weight is, well, weight is the force, the gravitational force, if you want, is the force on an object from the planet, right? Any force, the special forces that we give a special name, always define it in terms of what is it on and what is it by, right? So weight is the force on an object, right? By the pull, right? The force is either a push or a pull, so it's a pull on the object by the planet. Now, we also learned Newton's third law in the last lecture, right? So Newton's third law says that, well, if there's a force, so what is weight is really the force on the object by the planet. As far as I know, I live on Earth, right? So that would be by the Earth. Well, then there should be equal and opposite force on the planet by the object, right? Well, yeah, you might think if this is the planet, right? If it hits the ground, yeah, sure, they sort of collide, and there's definitely, if each one has a force on each other, just like if I push a friend that I don't like that much away from me, then if I exert a force on it, I will experience an equal and opposite force to myself. All right, good, but how about during the time of flight when it falls? Well, the planet exerts a force on this guy, but does this guy exert a force on the planet? How come we haven't talked about that? There's a missing link. Is Newton's third law apply over here? Did we just find a reason to break Newton's third law? Or if we did not, what on earth is that relationship? What is the counteracting part on that? So we have to look at that, and it goes under the very epic name of universal gravitation, right? So blame Newton for inventing that. But yeah, so those are the sort of the next two topics. But today we're going to basically just look at a bunch load of more examples. Okay, so that's our goal today. In particular, we'll look at all the classical examples that we can. All right, so all the classical ones you've heard about, starting with probably the one that turns most people away from physics more than any other problem, the infamous inclined plane problems, right? The inclined plane problems. Yeah, try to say that fast 5 times. It's even hard to pronounce. All right, these are not planes that are, these are not airplanes that fly at an angle, but just the slope that has an angle and something sliding down, right? So we'll finally tackle those. We'll look at another one. If that doesn't turn you away from physics, pulleys is the other one that will turn you away from physics. We'll look at that, but now I believe once you're armed with everything, all the knowledge you have, you'll be able to tackle these no problem. All right. And the other two that we will also look at is, if I can remember them, look at a very interesting idea of elevator physics. And that's really just a motivator to motivate me to talk about the concept of weightlessness. All right, so we'll explore these couple of things today, and we'll look at them one video at a time.